So here is a pictorial illustration of the problem. The problem is that you've got many users, you've got many movies, and you can put them into a matrix or table. You can also think of this as a bipartite graph, with the user nodes on the left, movies nodes on the right, and it's bipartite because only users and movies are paired up, and you can give weights to these links 1 up to 5. So there are many possible angles. First, we're going to view this as a table. Now, in this table actually is a little misleading because A is too small. There are only 48 possible entries. Okay, whereas actually we can have around 10 billion possible entries in the actual Netflix price. It's also very dense. You can see that about half of the cells are actually filled with actual rating data. It's a lot sparser in the actual Netflix price. So the size and the sparsity are actually not accurate. But suffice says to conceptually illustrate what the problem is. You're given these data points, which are 1 up to 5 integers, and whatever is the blank means that this user has not rated this movie. And she might have watched the movie or not, but there's no rating recorded. And you see 4 question marks. These are basically entries where Netflix knows the ground truth, but you and I, as teams entering into the prize competition, we do not. Or maybe we do, but we have to reserve it as the probe set. So in any case, when we train the data, we use the data shown here, and then when we test, or when Netflix tests, then they can use these hidden ground truth. If you just stare at this particular table here, you say, well, how do I predict these 4 entries? Maybe I would say, just look at this movie. Okay, if this movie is got a lot of high rating, just give it high rating, like 5.5. Or maybe this is 5.2. This is 4.5. Another good movie, make it 4.5. Okay, this one's 2.34. That's a tough call. Maybe I'll look at this row here. Okay, I'm trying to predict how would user 5 like movie 3, but user 5 seems to give 3.3 all the time. Maybe she also give 3 here. What about this entry? The movie 7 gets 1, 3, and 4. It's kind of diverse. And this user actually gave 2 and 4. So it's really hard to say what this might be. Okay, it could be 1, 2, 3, 4, 5. I don't know, maybe just give an average. Whatever is the average of all the entries here. Let's say the average is 3.5. All right, 3.5. It sounds a little like filling out a table in the Sudoku. Well, in what we just talked about, we actually touched upon a few intuitions. One is that certain movies are, in general, better made than certain other movies. And certain users are very strict graders or very loose graders. Okay, we have to take into account those things. We can also, when there's no other help, just give up and say, take the average of the whole table as the prediction. That's a very lazy predictor. So there's some intuitive understanding just emerging, but none of this is good enough to get you 8%. Not even close. You have to think a little harder than that. Okay. But in what we just talked about, we actually have touched upon what's so-called content-based filtering. In other words, just look at an individual column or row. Column corresponds to movie. Let's say individual column. Do not worry about what the other columns show. And this is similar in a crude analogy to the Google, if Google were computing a relevance score. But if you want to do importance score by looking at the connectivity pattern among the web page, or in this case, what the other movies showing tell about this movie, then you need to go from content-based to collaborative filtering. You say, why do I care about what the other movies are like? Because maybe certain movies are liked by a particular user. Okay? And as far as that user is concerned, maybe these two movies are very similar. And therefore, I would be able to say these two are neighbor movies. Okay? So if some user likes this movie, maybe she'll like this movie too. They're basically defining a neighborhood relationship between movies. Now, we could also do a neighborhood relationship construction for the users. If certain users from the different existing entries show their tastes are very similar, maybe then if user 3 likes a movie, user 4, even though she hasn't watched the movie, will like it too. This actually is what we intuitively do a lot of times. There's another idea, which is a little more involved, and we'll postpone it to advanced material part of the video, is to say that maybe there are some kind of feature sets about these movies. For example, is this a romantic movie or action movie, a thriller movie, a sci-fi movie? Is it long? Is it short? And so on. And these feature sets is a much smaller set than the set of possible movies. There might be 20,000 movies, but only about, say, 20 different genres. And I will try to extract the underlying reason why certain movies liked or disliked by some people. And these two are the two key distinct approaches of collaborative filtering: the neighborhood method and what's called the latent factor method. These latent factors are these feature set entries. We will focus on neighborhood method and then reserve latent factor method for the advanced materials. As we just mentioned, it's a large and sparse data. That's the big challenge. One solution is just look at each row and each column in isolation. It's called content-based filter. The other is look at the entire table. It's called collaborative filtering. Collaborative among the users and movies, I guess. And this is just like this one is a centralized computation. So we don't need distributed computation. And within collaborative filtering, there are two main flavors. It turns out these two are also interestingly connected, but we will skip that. It's in the textbook and advanced material. One is neighborhood method, the other is latent factor method. Along this way of going to neighborhood method, we'll take a couple of detours. One is going into a particular optimization problem called the least squares. It's one of the most frequently used optimization problem in many diverse fields, from control of airplanes to your remote, from how light bulbs are controlled on the factory floor to a lot of supply chains. It is used in finance and economic modeling. It is used in many communication systems. It is a hugely useful optimization problem. And it is a special case of something called convex optimization. So we will take about a 5-minute detour into defining a convex optimization, because this will be a recurring theme. We'll see this a few times later in the course. And we will actually not really have time to take a detour of two very important ideas to win, say, the first year progress prize. One is implicit feedback. If somebody have not watched or have watched a certain movie, that is also useful information, not just the explicit rating. And the timestamp, TUI, is also important. First, movies come in out of fashions over that period of 7 years. And second, different users also may have different moods on different days. There's a batch processing effect. If this user decide to rate the last 10 movies she watched on Netflix on the same day, those 10 ratings tend to have a different statistical distribution than if they were entered right after watching each movie on different days. Incorporating both implicit feedback and temporal dynamics would be important for you to get to, say, 8.5% improvement over sign match. But we will not have time to go through these. So our focus right now will be on the methodology of collaborative filtering in the neighborhood method.